Hi, Mr. J here with our lesson, hopefully about 10 minutes that you're going to do at home. And then we might have a little quiz next day just to see that you've watched this and did your best to understand the content of this lesson. It won't be too technical, but I want to make sure that you're watching these videos. So what are we talking about today? We're talking about how we prove lines are parallel, and it says I can ensure that two lines are parallel by construction, but also really by analysis, by looking at the angles and looking at corresponding angles or alternate interior angles, and using that information, using the angle information to prove that the lines are parallel. And this was done really 300 BC by Euclid, and he came up with something called the parallel postulate. And postulates, as we know, are things that can't be proven. And it was thought that you could prove the parallel postulate. So I want to get over to what is the parallel postulate. And but before I do, I thought I'd share with you this interesting building called the Cafe Wall Illusion. It's a little hard to see here, so I brought over another version of it, which you may have seen before. Let's move that out of the way and look at a version of this. And I like optical illusions, and just to look at this, it kind of makes your brain hurt a bit. But do you see these as parallel lines, and how can we prove that they're parallel lines? So I might suggest that you come and use maybe draw a line that you know is straight like that, and maybe we'll just move that right on that line there. Do you think these are parallel, or do they look wavy to you? So we're going to find out. So I'm going to duplicate that line now, and maybe I'll put it right here just to prove it, but let's move it out of the way. Do you agree that those red lines are parallel? And then move this in, and I think you see that it follows exactly on those lines between the boxes. And so these lines are truly parallel. And what we are going to do is try to figure out how to prove parallel with the use of a transversal, really focusing in on, say, corresponding angles. If this angle and this angle are congruent, so that's the converse we're talking about now. If these two angles are congruent, then the lines must be parallel. And we'll dig into that a little more. The first skill I want to talk about is to go over to Geogebra, and if we can do that. And that's just where I found that illusion. Oh, and a second illusion, this one called the Zollner illusion, which I think is pretty interesting. They don't look parallel again, and then if you hover over it, you'll see that the lines truly are parallel. Let's go over to Geogebra. I've done a little setup, but let's go back and just start from scratch so that you guys could do this on your own. And we're going to start with a line, and the parallel postulate says through a point there is only one line that's parallel to another line. So let's go ahead and see if we can find this parallel line that goes through this point. And we could certainly go right into here and use the tools, and I hope you'll see that that's parallel. But that's not our goal right now. That's drawing it so it's parallel and it's through this point, and it's a nice useful tool, but that's not what we're going to do. We're going to use some construction tools to do this. I hope you remember the compass tool or radius tool that we can put up in the corner. And I'm going to put another point on this line here. And what I'm drawing now is really a transversal. So this will be the transversal. And now we want to draw that line through C that is parallel to AB. And what we'll do is use our compass tool. And we're going to go to compass and use this as the radius and put one circle here and draw a second circle up here. And we will identify the points of intersection on all of these. You can see those 2 points are identified, and let's find the point of intersection of these. And I think it's useful to actually come back and draw this segment here, because that's a distance, and a compass is good at finding a distance. We don't need to know the number of it, but we're going to copy this and hang it, use the term hang it off of this to come down here, so that we get the same circle and chord up on this top figure. So now we'll draw another circle, but use this radius tool and hang it off this one up here. And let's see what happens. Let's find the point of intersection between these two. And can you see that this distance here is the same as this distance here? It might be useful if I change this radius. We have circles that are kind of the same size here, don't we? So I'm wondering, and it looks like the angle is the same size. Let's go ahead and make these circles look different in size, because I think that may highlight it a little bit better. So this circle around vertex F and vertex C are the same radius. Can you see that? And then I found the distance from I to H, and I brought it up and hung it off of point K, that point of intersection. And now I'm going to draw a line from C to N, and I want to see if this line that I just drew, and I'll change the color just to make it stand out a little bit, is that line parallel to AB. So they'll never intersect, and they have the same perpendicular distance to each other. And I like the mechanism here. You can kind of see how this is almost like a machine. All right? You see how I'm changing that? And I can change point C, and we can never get them to intersect. So we have successfully drawn a line through C that is parallel to AB. You can't really see that point A very well. But that was the first skill that I wanted you to be able to do. So I hope that worked for you. Let's move ahead and talk a little bit more now about, well, here's a little bit about Euclid, father of geometry, and the fifth postulate and the parallel postulate. In a plane, at most, one line can be drawn through a point not on the given plane, not through a point not on a given line parallel to the given line. Wow. But I think of it as when you have a point and a line, there's only one line that can be drawn that's parallel to that line. I also wanted to highlight for you guys something called a flow proof. And a proof in general, we've been doing two-column proofs, but a proof is any written document that produces a proof that's logical and deductive and uses postulates, theorems, definitions, and properties to make your point, to get to what you're trying to prove from a given. And flow proofs are actually really useful and interesting, even though we don't use them as much as two-column proofs. I wanted you to see what one looked like. So a flow proof uses boxes and arrows to show the structure of logical argument. And you could say that in a statement and reasons. You know, sometimes you don't know how the different statements relate to each other. But within a flow proof, you definitely can see the connections here. So let's just, again, a very similar idea to what we've been doing with proofs. You have the given, which is in the start. And what we're trying to prove is in the end. And then we have to fill in this middle, connect it together. But it really does help the reader, I think, when you have a flow proof, because you connect the ideas together. So A is parallel to B, and we would write that that is because it is given. And so we can put that in our first statement. 1 is congruent to 2. Why is 1 congruent to 2? And I hope you're getting used to some of these vocab words. What should we say for why 1 is congruent to 2? Vertical angles theorem. Keep it kind of small. Why is 2 congruent to 3? 2 congruent to 3. Well, they look like they are corresponding angles, and that's a postulate. So we'll put that in, corresponding angles postulate. All right, so that's going to be there. And why is 1 congruent to 3? Well, if you look through the other steps, you'd see if 1 is congruent to 2 and 2 is congruent to 3, then 1 is congruent to 3. Well, that means that's transitive. Transitive property of, and we're dealing with congruence, so I'll use congruence. So I wanted to give you one example. We'll see more of these of a flow proof. All right, but now back to parallel lines. So in our last section in 3.1, you would have seen that we had the corresponding angles postulate. We talked about these relationships and locations. And really, there was only one that was a postulate, right? This was the only postulate, and the rest are theorems that we could prove. And we did just do a proof of a theorem. That's what this one over here was. This was a proof of the alternate interior angles theorem, and we used a postulate and another theorem to make our proof. So all of these theorems here could be proven if we wanted to. Now this section, 3.2, is to prove that lines are parallel. All right, so whenever we are wanting to prove that two lines are parallel, maybe we want to prove that M is parallel to N. Within that proof, actually the very last line of that proof will be a converse, okay? Because the converse here are what we use to prove parallel. If two lines are cut by a transversal so that the corresponding angles are congruent, then the lines are parallel. So see the last line of each of these, then the lines are parallel. Lines are parallel. Lines are parallel. So whenever we want to prove that lines are parallel, we will use a converse. Okay? We'll get into a little bit of practice of this too. Okay, so let's go into this a little bit. Let's read it, which I should have done before in that flow proof to see if it makes sense. But right now, whenever you're doing a proof, read it and see if it makes sense. So Belinda is tiling a floor using quadrilateral tiles. Okay, four-sided tiles. Regardless of the color, the central tiles are identical, congruent. Okay, they're congruent. She knows that angle 1 is congruent to angle 2. 1 is congruent to 2. All right, she knows those two are congruent. She wants to prove that this line is parallel to this line. All right, so as I look at that, I'd say, okay, this line T will be the transversal. 1 and 2 look like alternate interior angles. And if they're congruent to each other, then yes, L must be parallel to M. That seems okay to me. So why is 2 congruent to 4? Well, that looks like that's a vertical angles theorem. Why is 1 congruent to 4? Well, they seem to be corresponding angles, so it'd be a corresponding angle postulate there. And then what would justify that L is parallel to M? And so if 1 is congruent to 4, that would be the converse of the corresponding angles postulate. Whenever we are trying to prove parallelness, we will use converse. All right. So if we have a quiz tomorrow, the thing I might ask is, when do we use a converse? I might ask, what is a flow proof? What is the nature of a flow proof? Okay. And then I have one more topic here, and then maybe one more practice that we're going to do. How long is the video now? We're about 13 minutes. So the transitivity of parallel lines, well, you know that word transitive now. Transitive means, we use equality, A equals B and B equals C, so A equals C. This I think will make sense to you too. It's a property, so it's not something we prove, but it says that if A is parallel to B and B is parallel to C, then A is parallel to C. And I think that follows the idea that we've been talking about with transitive. All right. And then they had one more practice here that's right out of your textbook. I'm not going to do this now. I think the video is getting a little long. It's something I'd like you to look at and that we can talk about in class. And it's one of those Mad Libs fill in the blanks kind of proofs that a lot of it's given, given meaning the boxes are filled in, and then you have to just do a few things to finish it. So that's our brief 13-minute lesson, 14-minute lesson that I expect you to watch. And then in class we are going to practice proofs. Okay? Thanks.